Hello everyone, welcome to this new tutorial. Today we'll draw shapes in the window we created in the last tutorial. If you want to follow along, you can watch the previous tutorials on YouTube and download the source code on itch.io. Okay, so let's get started. The first thing we need to understand is how we are supposed to draw things in the window. In order to do this, we need a buffer. A buffer is just some piece of memory that we can use to process the pixels and the colors and then send to Windows so it can display it. So that configures the three steps we need to do. We need to get the buffer, fill it, and then send it to Windows. And this filling and sending to Windows will be done inside our game loop. At the end of it, we'll have a picture or a frame. And when we play these pictures in succession to the player, it will look like animation. And since we'll simulate the world and change that every frame as well, it'll look like an interactive animation. So how are we going to get the buffer? To get that piece of memory, we first need to know what size is our window. Since the player may change the size, for instance making full screen or windowed, or having different display size, we'll have to do this every time the size of the window changes. If you remember from last tutorial, we can process the window messages inside the window callback function we created. So let's go there. So in case we receive a WM size message, it means that the window changed size. And now we must know the new size by getting the client rect. This function takes the window and a pointer to a rect struct that contains the left, right, up, and bottom values. Now the width and height can be easily calculated by subtracting the right from the left and the bottom from the top. Okay, so now let's get our memory. Our buffer will contain width times height pixels. And our pixel will be a 32-bit integer that's capable of storing 8 bits of red, 8 bits of green, 8 bits of blue, and 8 bits to pad to a 32-bit word. So that's what the buffer size will be. Width times height times the size of an unsigned 32-bit integer. Now let's talk briefly about the stack and the heap memory. When our program is launched, the operating system can give us a bunch of memory for our program to use. This memory is called the stack. Every time we create a variable, the variable is inserted on the stack. And every time that variable goes out of scope, the variable is popped from the stack. But in this case, we want our buffer to persist this stack. And we also need to free it and reallocate it whenever we need a window of a different size. So in this case, we're going to ask Windows for a new memory. And this memory will come from the heap. And how do we do that? Well, most people use the C runtime library function malloc. But since we are in the Windows platform layer, we can use a more specific Windows-only function like virtualloc. It takes in the address we want to create, in this case it doesn't matter, the size, the types, memcommit and memreserve. And we want to read and write from this page. And this memory we're going to take is a void pointer, which means that it's a pointer to somewhere in memory that we don't care about the type. Since we need this pointer to be persistent across different functions, we're going to create it as a global for now. And we're also going to create the width and height as globals. But what if the player changed the size again? In this case, our buffer memory already has an allocated memory, but it may be too small or too big for our needs. So we have to check if our pointer already has some valid memory, and if it does, we should free it first before allocating a new memory. And we can pass 0 for the size and memRelease for the last parameter. Okay, now let's see what we have. I'm gonna run with Control F10. So I'm gonna run the game until it reaches this line that I'm currently on. Okay, so when the window first pops up, we have a window size message. And let's see the values. Our width is 1264. Our height is 681. That looks about right, because there is a small border from the window. And since we don't have any buffer memory yet, we're not going to free anything, but we are going to alloc. Now see that the buffer memory now holds a memory address like we discussed last time about pointers. We can open a memory window from the debug section. Then if we take a look at this address, it returns a lot of memory. It's already cleared for us. Okay, so we're going to put a breakpoint here using F9, and we're going to press F5 to continue the game. So the next time this line is executed, we're going to stop again. Okay, so we have our windows like we did last time. Now let's make it full screen. So again, we're going to run the size we're going to get the new width and the new height, but this time, and the new size as well, but this time our memory is already occupied. So first we're going to free the memory. See here in the memory that it changes to not valid in this case, but we're going to allocate again. And the new address we have is already clear for us. Perfect. Now that we have the memory, we need to send it to Windows and ask it to use it. And we're going to do it in this stage, after we simulate the world. The function for that is stretch di bits, and it takes a lot of arguments. First of all, it needs a handle to a device context. Whenever we create the window, we can get a device context, which is the reference that Windows use in order to draw to it. So let's create one here. All we need to do is pass the window to the getDC function and we get that handle. We need the x and y dest, the width and the height, in this case going to be the whole window. The source x and source y and source width and source height is going to be the same thing because we're going to do a one-to-one copy. And here's the memory that we're going to pass as the pixels. And now we need a pointer to this bitmap info struct. This bitmap info holds a lot of information like what does our pixel look like, what does the compression look like, so Windows can know exactly how to copy that to the video card. So we're going to have to fill that. And the best place to do this is in the size message. We're going to create a global for the bitmap info as well. And if we go to the documentation, we can see all the fields that we need to fill. In this case, they're inside the bitmap info header. There they are. The size will just be the size of the info header, just so Windows knows what version we are using. The width and the height we already have. Planes must be 1 for some reason. The bit count will be 32, remember? 32-bit unsigned integer. And the compression will be RGB. We don't need the rest. So now we can pass the pointer here. The usage will be DIB RGB colors, and the operation will be a source copy. Now let's see what we have. See, now we have a black screen. And even if we make that full screen or change the size, it's still a perfect black screen. Why is it a black screen, do you remember? Because the memory we got here was zeroed out. So now all we have to do is change the colors of our pixels. Let's do this. So I'm going to iterate through all the height and the width pixels. Now I'm going to create a current pixel pointer. It's going to point the pixel that we want to fill. It's going to start out as the first pixel in our buffer. And for every pixel, I'm going to change its color to a nice orange and increment it to point to the next pixel. Oh, that's awesome. Just look at that. And if you change the size, it works perfectly as well. We can do more interesting stuff to the pixel, right? Instead of changing it to orange, let me try to make some cool gradient colors. Look at that. You can certainly play around with this as well to learn and also have a bit of fun, right? Awesome. And this is the foundation for the game. The inputs, the simulation, and the rendering. Everything now is working as the first version, and we can start building on top of it. Now let's take a moment to clean up a little bit, because we threw a lot of code without thinking just to get this first version working. So let's change all these variables to a struct. And we can make now this struct a global variable. And change it here. Okay, let's see where we missed. Yeah, this one we don't need to. I'll also make the bitmap underscore info, let's see. Okay, perfect. And I'm also going to change this function to be in a rendering file, so we can use that whenever we need, like draw a rectangle, clear the screen, things like that. I'm going to create a new source file, and I'm going to call that renderer. And I can create a render background function. Now, how is this file supposed to know what's in the other one? Let me take a little time to explain to you how the compilation actually happens. The most usual way to compile a program is to take all the CPP files, compile them into an intermediate .obj file, and then link them together into the executable. So we have all these different files compiled separately. However, today a lot of people are trying what's called a unity build. It's when you include one file to the other, instead of compiling them separately, and then you just send one huge file to the compiler, and you can do in one run the compilation and then the linking. That's what we're going to do. Not only makes it easier for the files to see one another, but it also makes compilation really faster. So I'm going to include the renderer file up here, and this include will just copy the code from the renderer file to this file. But now we don't need to compile the render, because it's already included on the Win32 platform.cpp. So I'm going to right-click the file, choose Properties, and select Exclude from Build. I'm going to include the renderer after we declare the global render state, so that the render file can use it. Okay, we're back to normal. But what are our functions we need? Let's write the usage code first. In the game, for instance, we want to be able to clear the screen so that the last frame doesn't interfere on this frame. And we probably want to take a color as well. We also want to be able to draw rectangles, which is the most simple shape, by passing, for instance, a position and a color. Now let's program those functions. The clear screen is pretty easy, right? You can do it yourself. If you feel up to the challenge, try pausing the video and creating the clear screen function. Well, let's do it now then. It's going to be the same thing we did up here. We set the current pixel to the first pixel, then iterate through all the width and the height pixels, and then set it to the color. I'm going to create an empty procedure for the draw rectangle for now. Just taking the parameters for now. And let's see what we have. Good, our clear screen works. And what about the draw rectangle? It's pretty much the same thing, but instead of setting the first pixel at the very beginning of our buffer, we need to offset that by the starting X position and the Y position times the width of our buffer. So we get to the first pixel. And for every row we change, we're going to get a new first pixel, and we can just increment that like we did in the clear screen function. So let's see. For every row we're going to draw, I'm going to set the current pixel to the memory. I'm going to offset the first pixel by the first X pixel, and the current Y pixel times the width. Instead of going through all the pixels, I'm going to start at the Y0 and go to the Y1. The same thing for the X. Now let's see what we have. Nice! We have a red rectangle. Well, the color is pretty bad. Let's change it. Oh, now we're talking. And if we change the size, it correctly updates. Oops, but we just crashed the game. Let's see what happened. We tried going all the way to the Y500, but our height doesn't go that far. So we need to clamp the X and the Y. So its minimum value is 0, and its maximum value is the width or the height. The clamp function is really simple. It takes a minimum, a value, and a maximum. And if the value is less than the minimum, we return the minimum. If it's greater than the max, we return the max. Otherwise, we just return itself. Now it shouldn't crash if you try writing off screen. No, we don't. Perfect. Now let me organize this function a little bit better and create a utilities file. And we also have to exclude it from the build like we did before. And since we created utilities, we might as well make some utilities, right? We can type def unsigned int to u32, so it's way easier to type. And we should also include the file, right? Perfect. Now since we did the u32 type, we might as well do all the others, right? Another useful utility we can do is the static one. Since all our files are being compiled into a single one, all of them can be static, which means unique to that compilation unit. But instead of just typing static all over here, and here as well, we can define to be a more easy to understand name, like global variable and internal. And all these functions can be static. We don't need this one anymore though. And these are global variables, which is going to make it easier to search. And we're still good. And there's one last thing we want to do to our renderer before we call it a day. And that's to make it pixel independent. See the problem we have. This is the size of the rectangle when the player is playing it in a 1280 by 720 screen. However, if we make that screen smaller, the player occupies the whole screen. But if we make that even bigger, the player occupies a smaller part of the screen. And we want that to be consistent. In other words, we want to be able to communicate in a unit that doesn't change when the size changes. So this draw rectangle is actually draw rectangle in pixels. We need a new one. Let's make it receive an x and y floating point position, as well as a half size x and y. And now we want to change from this unit to pixels. And we also want to center them. So 0, 0 is actually right in the center of the screen, instead of the bottom left. And then we can just call the draw rect in pixels. Oh, and we should also take a color. Let's just do a simple mapping for now and generate the min and the max points. And all we need to do is either subtract or add in the half size. Now let's try calling this function. We'll make the half size be like 1020. Let's see. Okay, but right now it's still in pixels. But how are we supposed to convert that? Well, if you just multiply the position and the half size by the screen width or the screen height, we're going to have a unit that is relative to the width or the height, no matter the value. For instance, 0 would be exactly 0 screens, and 1 would be 1 width, for instance. So if our player is 0.2, it's going to take 20% of the screen, no matter what the screen size is, and that's precisely what we want. So let's do this. Let's see what we have. Yeah, well, now it's just huge, right? But if we make it like 0.2, the half size should be 20% of the screen, so it should take a little bit less than half. And let's make it start at 0.5, 0.5. So as you can see, it takes approximately a little bit less than half of the screen, and if we increase the width or decrease it, it's going to change the size. That's perfect. Now one question is, should we use either the width or the height here? Let's change to the height and see the difference. Now whenever we change the width, nothing happens. But if we change the height, it gets smaller or larger. So in this case, if the player is playing at an ultra wide display, you'll be able to see more of the world. That's what we want. However, if the player is playing in a 16 by 10 display, which is a little bit more square than a 16 by 9, he'll actually lose a little bit of the world. That's not very cool, but we have to stick with one. Let's stick with height for now. But we also want to offset that to the center of the screen, right? It's going to be way easier to control. At this point, we are already in pixels. So all we need to do is to add to the x and the y half of the width or the height. So now if we pass 0, 0 there, it should be centered. It is. Now that's perfect. So now we can start populating our ruler just for fun with small squares. Pretty cool, right? However, it may be a problem to keep typing 0.0 stuff every time. I think it would be easier to have like a scale multiplier. So that 100 will be one full height, and not 1. And let's change the values. Awesome! Now we are in a great position here. We are already capable of drawing shapes in the screen. And that's enough to make the game, right? But now we need to control the shapes with the keyboard, for instance. And that's what we're going to do in the next lesson. I hope you enjoyed this one. If you have any questions, let me know in the comments below. You can download the source code to follow along the series. If you're feeling extra adventurous, you can try improving the game before the next tutorial. One idea is to make the world to pixel conversion inside the render not fixed on the height, but based on the aspect ratio. So if it's wider than 16 by 9, use the height as the base axis, like we're doing now. But if it's taller, use the width. How about that? Anyway, I hope you learned a lot, and I'll see you next time.